work with Chebyshevs theorem just a bit more. So remember that Chebyshevs theorem does not depend on the random variable or the model that the distribution of the random variable at all. But we do need to know, in order to use Chebyshevs theorem, we need to know the mean, and we need to know the standard deviation or the variance. Okay, so let's take an example of that. So let x be a random variable, and all we know about it is that it has a mean of 100 and it has a variance of 4. If we're going to observe many x values, and if we want to state that at least 96% of the observed values are likely to fall between 100 minus k and 100 plus k, in other words, we want to know, we want to have at least 96%. We want to know how far outside of the mean, how far from the mean we have to go in order to be sure that 96% of the time the observations will fall within this range. We want to know what that range has to be. What value should we take for k? So how far out do we have to go in order to be sure, in order for Chebyshevs theorem to tell us that at least 96% of all the observations will be in that range? So how big a range do we have to take? Okay, to ask that at least 96% of the observed values fall between this and this is equivalent to asking that each observed value fall between this and this, with probability at least 96%. If we choose h in Chebyshevs theorem so that this equals 96%, remember that this gave, remember if h was 2, then the probability was 75%. If h was 3, then the probability was 8 over 9. So in other words, we want to make this equal to 0.96. So we want to know what h that has to be. So we just say this should be equal to 0.96, and we solve for h. So we get this, we move them over, we get this, we get h equals 25. I'm sorry, h squared equals 25. So taking the positive square root, we get that h equals 5. So if we want to be 96% sure that all the values will fall in a particular range, then Chebyshevs theorem says that we have to go out 5 standard deviations in each direction. So if 100 was the mean, we have to go 5 sigma to the right and 5 sigma to the left, that range. And we were told that sigma squared was 4, so sigma was 2. So that means 5 sigma means what? It means 5 times 2. So we have to go 10 units out from 100 and 10 units down from 100. In other words, we have to go from, then the range is between 90 and 110. That is, we're 96% sure, I should say, that values will fall in that range. Or another way of saying that is, the probability is 96% that the values will fall in this range. Okay, now, since the theorem has such broad application or applicability, it's natural to expect that for some random variables, this estimate may be rather poor. So, it may be that this says this is the minimum. That is, for example, in this case, at least 96% must be between here and here. But if we know more about the random variable, we may be able to say not just 96%, but maybe 98% or 99% must fall in that range. So they say it is in fact the case that for many random variables, the probability is much greater than this of obtaining a value within h sigma units of the mean. For this reason, statisticians usually regard this estimate, for example, 96%, as very conservative. It's always true, so it's at least that, but we could if we know more about the random variable, which we'll see in the next two sections, then we'll come up with an even stronger estimate, or an even higher percentage. Okay, in this next example, they're going to tell us that the mean of a random variable is 750, and they're going to want to know how sure are we that observations will fall between here and here, and that distance is 15. So we need, first of all, to know how many standard deviations is this number from 750. So we need to know the size of the standard deviation. Well, it turns out that the standard deviation for this problem is 10. So that means this is 15 regular units, or real units. So how many standard deviations? It's 15 over 10. So it's 1.5 standard deviations above, and this is 1.5 standard deviations below. So we're going to be asking, we're going to say that h is 1.5 standard deviations, then we're going to say what percent of the data has to fall within 1.5 standard deviations. So that means h is 1.5. So we can just put that into the formula. We get 1 minus 1.5 squared. Turns out to be 5/9. So we're going to know that 5/9 of all of the observed values must fall between here and here, which is what they use here. But let's read the problem. A certain high-quality commercial light bulb has an expected lifetime of 750 hours, and the variance is 100. So it's 750, but the standard deviation is 10. So now they want to estimate the probability that one of these light bulbs will last between 735 hours and 765 hours. So between here and here. So what's the probability that it will be in that range? So we said that that's 1.5 regular units. So that's 1.5 standard deviations. So Chebyshevs theorem will say that we have to have at least 5/9 of all our light bulbs will be within this range. Or we can say it another way, that the probability that our bulb, that one given bulb, will be within this range is at least 5/9. Okay, the second part, part B. If 20,000 of these bulbs are installed in city streetlights, how many bulbs do you estimate would need to be replaced between this and this hours of use? So then it's just going to be 5/9 of them will be within this range. So how many will be, well, what we really want to know is how many will fail. So how many are less than this, I guess, is what they want to know. No, sorry. They want to know how many will last in this range. Last means they'll die within this range. So we know that it's 5/9 of the total. If 20,000 are installed, then it's going to be 5/9 of 20,000, which is 5/9 of 20,000. This many bulbs we will expect to fail between the 735th hour and the 765th hour. Okay, let's look at some of these exercises. Let x be a random variable with mean 0 and variance 16. So the standard deviation is 4. In each part, express the distance between A and the center in sigma units, or standard units. So if we said that mu is 0, so if A is 4, how far is A from 0? Well, obviously it's 4 units from 0, but that's not what they're asking. They're asking how many standard units is it, or sigma units. So, or how many standard deviations is it from 0? So we said the standard deviation is 4. So this is 1 standard unit from 0. This one is how far from 0? It's 2. This one is 6 over 4, so it's 1.5. And this one is 11 over 4, or minus 11 over 4. whatever that is. I guess it's minus 2 3/4 standard units below. We would say it's 2 3/4 standard units below 0, but they say distance, and it's just 2 3/4. Okay, let's do the next one. Let x be a random variable with mean 5 and variance 4. In each part, express the... Okay, so this is the same question. Let x be a random variable with mean 10 and variance 9. In each part, the distance between a and the mean is expressed in standard units. Find the value of a. So now they're just reversing it. They're telling you how many standard units a is above, and they want you to say what a is. So if a is 2 standard units to the right of the mean, so the mean is 10, and the standard unit is 3, if it's 2 of those above 10, then it's 2 3s above 10, that's 6 above 10, so it's 16. And this one, it's 3.5 standard units to the left of 10, so 3.5 times 3, so you can, whatever that is, okay, you can do that. Okay, let's do number 4. Let x be a random variable with mean 0 and variance 4. Use Chebyshevs theorem to estimate the probability that x takes on the value within 1 unit of the mean. So that's one we didn't cover, within 1 unit of the mean. So that is using Chebyshevs theorem. What do we get? Here it is. It's going to be at least this amount. So what do we get? At least 0. That's obvious, right? Because it's 1 over 1 squared. So that's 1. So it's 1 minus 1. So that's 0. So it says that at least 0% of the data is in that range. Well, that's useless because, of course, at least 0% will be there. So when h is 1, it's not interesting at all. But, okay, let's do when h is 2. If it's 2, we already did it. It's 75%. And if it's 3, we already did it. It was 8/9. Okay, let's go to the next one. Let x be a random variable with mean equal to 12 and variance equal to 9. What's the probability that x takes on a value between 9 and 15? So now we want to see how far are 9 and 15 from 12. And obviously they're both 3 units from 12. And the standard deviation is also 3. So we're talking about just 1 standard deviation. So we're back to this problem. So we can say, according to Chebyshevs theorem, that at least 0% of the probability is in that range. So that's not very useful. Okay, how about this one? 11 and 13. So that's a little bit more. That's I think that's going to be even interesting. I never did that one. But anyway, that's going to be at least 0 also, right? Same thing, actually. But how does that work? Yeah, it's going to be at least 0, so that's not useful. How about this one? Between 0 and 24. So 0 is how many standard units below 12? So it's 12 real units. So, but the standard deviation is 3, so it's 4 standard deviations below, and 24 is 4 standard deviations above. So we put h equals 4. So if you remember, it was 1 minus 1 over h squared. And h is 4, so it's 1 minus 1 over 4 squared. So it's 1 over 1/16. I'm sorry, 1 minus 1 over 16. So that's 15/16. So the answer would be 15/16. Okay, let's just do one more. A camera used in a weather satellite has an expected lifetime of 900 days. So a weather satellite flying around in space, and has a camera, and the camera doesn't last that long. It lasts about 900 days. It's a little bit less than 3 years. and the variance for the lifetime of the camera. So like if you had a lot of cameras, some of them would last more than 900 and some of them would last less than 900, and we're saying that the variance is 81. So the standard deviation is 9. So we're saying that like sometimes they last 900 plus 9 and 900 minus 9, or maybe we'd say 2 times 9 and 3 times 9 and so on. Use Chebyshevs theorem to estimate the probability that this camera will live between 870 and 930. So how do you do that? 870 is what? 30 units below 900. And 930 is also 30 units, but above 900. So 30 units, we have to think about 30 units. So how far is 30 units in standard units? So we know that the standard deviation is 9, so it's 30 over 9. So I don't know what that is, but so I'm not going to work it out right here. But I'll just say it was approximately 3. 30 over 9 is approximately 3. So that if it was 3, then what would we say in order to estimate the probability that the camera will live between this number and this number? If these numbers were 3 standard deviations from the mean, then we would put h equals 3 into the formula, into Chebyshevs theorem, and we'd get 1 minus 1 over 3 squared. So that's 8/9. Okay? But it's not exactly 3, so you have to do a little more calculations. Okay, that's the... Well, here's some more problems. And next time we're going to cover now a specific type of random variable called a binomial random variable. And we're going to be able to, once we define what we mean by binomial random variable, then we'll be able to make stronger estimates than we could by just using Chebyshevs theorem. We could use Chebyshevs theorem because a binomial random variable is a type of random variable, and Chebyshevs theorem applies to all random variables. But once we know it's binomial, once we have sort of more information about it, then we should be able to take advantage of that more information and make a stronger statement, which we will be able to do. But first we have to understand what's meant by a binomial random variable. Now you've already seen binomial random variables, but we didn't call them that yet. So we're going to talk about types of random variables that are binomial, and we'll see that in the next section.